Hello community, let's talk about multi-agent devices that are intelligent, you're not gonna believe it. Two cases. At first we look at new financial investment AI and then we will look at cybersecurity AI. So, financial investment, you know it, this mastery. We're looking here to our titans, we look how they invested, we try to copy their pattern, we have imitation learning and building sophisticated algorithm to replicate the historical trade patterns. But whenever we develop this system then and we bring it to the financial markets, those AI models frequently stumble. Because there is a blind spot in the traditional financial AI, it is the neglect of the strategic interaction of the market dynamic. Now, you know that financial markets are a dynamic interplay of strategic agents. So each participant, from the institutional investors to the hedge funds, to the individual trader and to automated algorithms, they all operate within a web of interconnected decisions. So individual actions ripple through the system, influencing and being influenced by the choices of others, creating an inherent uncertainty that cannot be captured by the simple replay of the past. So therefore, we have now a challenge in front of us. And we will apply now the mathematics of game theory for the new AI investment machines. So we will have a look at the concept of a correlated equilibrium. This transcends here the simplistic assumption of an independent decision making that we find in the Nash equilibrium. Because this correlated equilibrium acknowledges the presence of coordinating signals, a whisper of news, a shift in the risk probabilities of the market player to guide the actions of all participants, creating now here this interconnected behavior that our AI should anticipate. So, we know that the financial markets are not static. So there are stages where the agents have to adapt, anticipate, and respond to each other's moves, constantly rewriting the rules of engagement of the market. So therefore we will shift our code implementation now from the what we call value equivalence in computer science. Main point is that we just mirror the past performance of experts. We're trying to find patterns in the financial market. When we move over to regret equivalence, and I will give you the definition and explain this in detail. Because this new objective now explicitly acknowledges here the dynamic nature of strategic interaction. And we are here now with a mathematical optimization problem. We seek to minimize the potential loss that arises from failing to anticipate the actions of others, particularly when they deviate from the expected behavior. And this here necessitates the ability to reason about counterfactuals. What would have happened had we chosen a different path, considering the potential responses of other agents? It sounds a little bit complicated, and it is complicated, but luckily we have a formal mathematical framework for this. We're talking about Markov games, a specific regret gap that we will calculate within the context of a Markov game. So we require new algorithms and new computational formulas. We will have a look here at the latest research and you will discover new two algorithms, MALICE and BLADE. And those two algorithms were written especially designed here for this regret minimization task under dynamic market conditions. MALICE will operate under a coverage assumption of imitation learning, I will explain to you in a minute, while BLADE will utilize here a variable expert to gather counterfactual information. And this expert can be a real human expert, or it can be, another AI system with a knowledge of some particular trading information. So we go beyond patterns in historical data. Now, the unique selling point here is beyond mimicking past towards a system that can reason about the motivation of others, to anticipate potential market disruption and dynamically adjust our strategies to minimize this new regret gap that we will introduce here. And yes, this is a real complex task. And yes, we have to take care about a lot of potential. This could have happened, but our mathematics is now able to deal with this, and our AI systems are now able to deal with this. So this is now a new paradigm, rooted here in the science of the strategic interaction, game theory. And this offers here a profound shift in how we approach now financial investment decision making. It acknowledges the inherent limitation of the prediction, and it embraces the dynamic nature of our financial markets. But if you say, hey, financial investment, this is not my thing, maybe cybersecurity is what you are interested in. Now, we have a beautiful example. Imagine a system to prevent the CrowdStrike and the Microsoft event that happened about 2 weeks ago of global IT outage. Now, listening to the Australian news on that day, CrowdStrike, the error started in Australia and it moved around the world. And it moved around the world with the sunrise slowly happening in all parts of our beautiful globe with the morning update of the Microsoft machines. And you know, it is not that we had just a fraction of a millisecond to react on a cybersecurity threat. Microsoft, the announced global leader of AI with hundreds and thousands of GPU in its cloud data centers, they could do nothing. They just had to watch it happen in real time. And it's not about seconds, it's not about minutes. They had hours. And they could do nothing. And now the idea is simple. Hey, is it the task of your company, or maybe of your nation, to have your own cyber defense AI system? Because if an AI system would have been active and detected that something strange starts in Australia and then moves over to Indonesia, comes over to China, then India, and then it's approaching here the Far East. It's coming to Europe, and then it comes to the US. You know how many hours he had to react to prevent this from happening? So there's an immense potential for a cyber defense AI, but we have to build it, we have to code it in a particular way. So let's have a look what we do. Now, you know, whatever cybersecurity we use here, the battlefield is far more dynamic than everything that we have on our training ground. So this highlights the critical limitations of our traditional approaches to the AI-driven cybersecurity. It is our reliance on the value replication. We just here more or less mimic the past successes. But our AI systems struggle to adapt to the new threats or anticipate the action of adversaries who actively seek to outsmart our defenses. So the defender, locked in a reactive cycle, can only respond to attacks that have already happened in the AI system, leaving now the system vulnerable to novel or evolving threats. So what we have to do, again, we have to shift from the value equivalence, a term in computer science that we code, and this is our main metric, but we only replicate here the performance of the human experts, and we have to move over to a much more sensitive metric to regret equivalence, and then an optimization game of regret gap minimization, where the goal is here to minimize the potential damage from failing to predict and prevent novel attacks that were not in our original training dataset. So what we do, we need a new AI system that can anticipate the attacker's motivation, predict all their potential actions that they can take, and proactively deploy countermeasures to minimize the potential consequences of being wrong. So here again, you might say, but how can we code this? This does not exist yet. Yes, I know. But I'm going to show you the latest research in AI that we draw now on mathematics and physics, and we will imply it on the principle of a multi-agent imitation learning system, where we focus here on minimizing the regret gap, it's a mathematical term, in a Markov game. In the Markov game, you know, this is a formal model for strategic interaction. And this new framework will allow us to explicitly consider now the attacker's agency, recognize that their actions are not random events, but strategic choices driven by their own goals. And if we would have now this mathematical models, we just need here the computer infrastructure to execute them. And again, we have now two new algorithms, MALICE and BLADE. And I already introduced you to them. And they work here now as a security AI machine, allowing the AI system to actively probe for insights into how an expert would respond to a novel attack strategy. And here this expert can be a human or an artificial intelligence expert. And again, we have simple mathematical terms in a theoretical analysis to minimize the regret gap. So this means when faced with some novel or unexpected attack path vectors, the AI defender can still make informed decisions that minimize the potential damage. So therefore we understand we need a new way forward to a new secure digital world after what happened with the global IT outage by Microsoft. And we need new networks that are resilient, but resilient not only to the known attacks from the past that are now in our training data, but also to evolving tactics over ever-adapting adversaries. And you might say, how can we do this? And there's a beautiful answer for this. And you will have noticed that about a month ago, I was talking about multi-agent reinforcement learning. And now, since the last 3-4 videos, I talk about multi-agent imitation learning. And before we enter now, you might say, what's the difference? When to apply what? Now, it is rather easy. The reinforcement learning, you know, the agents, our AI agents, our VLM, LLMs, whatever we have with memory and agency, they learn through trial and error. This is it. This is the main event. And they receive feedback from the environment in the form of rewards or penalties. And they are calculated here based on their own actions that have an impact on the environment. So they explore their particular environment, experiment with different strategies, and iteratively update their own policies, how to do and what to do, what actions to choose to maximize their cumulative rewards. This is reinforcement learning for multi-agent systems. Now, imitation learning is a complete different game. Here, our intelligent AI agents learn by observing and mimicking the behavior of an expert demonstrator. The expert demonstrator can be a single AI system, a single human, or a group of humans. It can be a complete compute cluster system that behaves in a different way, or it can be something of a scale of a nation. But instead now of receiving explicit reward, and we define a reward function for a system, now our agent in the imitation learning phase, they aim to match the expert actions in all the different various situations that can happen in our environment. So you see, it is a different approach. Please keep this in mind when we move forward. Plus, if you think about this, the reinforcement learning with multiple agent environments tackles here the challenge of learning the optimal policies in a complex, dynamic environment without prior knowledge. Yes, you have a starting position and you have certain boundary position, but you do not have a successful path forward. Now, this is different with imitation learning, where MALE addresses here the challenge of efficiently transferring expert knowledge to our agents when we have a problem to find an explicit reward function, because there are no reward functions that we can think of, or maybe they are so difficult we cannot code them, or we cannot even define them. So what we do in those cases, multi-agent imitation learning. Now we reduce the complexity of doing everything in our environment, in our defined environment, and we focus it only to the actions of an expert system, and we try to to understand and optimize those actions. This is it. That's all there is to it. So let's focus now on MALE, Multi-Agent Imitation Learning. What is it in detail? It's a technique in artificial intelligence where a system learns how to behave by observing and imitating the action of multiple experts or other agents in a shared environment where our AI system has access to. Simplest case here, imagine a group of robots on the left side watching a team of humans on the right side performing different tasks. And now each robot tries to understand, hey, what can I do if I see the expertise of those individuals in the way they interact, how they interact to reach their goal? This is an amazing thing if you want to code this and enable an AI system to learn this behavior. To be a little bit more formal, in my last video, I talked here about an environment where we have multiple agents, vision language model, vision language action model. We have a Markov decision process happening in all of these diffusion systems, or maybe we have LLMs, or maybe we have transformers, or maybe we have diffusion transformers. Whatever it is, we know that those AI agents operate within a shared environment for a common goal, and we know where their decision and actions, how they affect one another. And now the primary mathematical framework we will use in this video in MALE can be described using elements now of game theory and decision-making under uncertainty. And this is commonly modeled through the famous Markov games. Now, I went and I looked for the original publication and I found it. Look here. Communicated by John von Neumann, 17. Juli 1953, Princeton University, Stochastic Games, Shapley. 1953. 6 pages, 6 small pages. And in 1953, stochastic games were invented. And this stochastic refers to processes that involve randomness or probabilistic elements. In other words, stochastic processes are those that are inherently unpredictable because they are influenced by random variables or change. If we move forward now to 2024, what is our Markov game definition today for my green grasshoppers? You have more or less 4 important elements. You have the states of the system. This is all the possible configuration that you can think of a specific environment that you act on. Then we have the actions, the choices each AI agent can make in a given state. So each agent I has its own action space, AI, and the joint action space of all the different agents that are interacting now is mathematically a Cartesian product of all the individual action spaces. And now you see, oh, wait a minute, this is gonna be a little bit complicated, no? Complexity goes up rapidly. Well, this is the beauty. But now we have the computer infrastructure thanks to AI. Then, of course, we have the transition function, defines how the environment transitions from one state to another state based on the current state and the actions taken by all the different agents. It's typically a probabilistic distribution, T, where our delta S represents here the set of probability distribution over the states. And finally, the reward function. It defines the reward that each agent I received based on the current state and the action taken by all the other agents. So each agent has its own reward function, or reward I, where R is, for example, the set of the real numbers. So you see, with Markov games, we now model the interaction between multiple agents and the environment. And a Markov game is nothing more that we extend the concept of a Markov decision process I showed you in my last 2 videos to a multi-agent scenario where multiple agents make decisions simultaneously. And now we have to master this chaos and we have to code something and we need some beautiful new ideas how we can cut through this and implement an AI system that is learning. This Markov game is a natural framework for modeling and mathematically solving here our multi-agent imitation learning, our MALE problems, including here the application of MALICE that I already introduced you just by the name. And there are several reasons for this, why it's such a beautiful implementation framework. First, we have multi-agent interactions. So our Markov game explicitly models the interaction between the multiple agents, and they capture the influence of each agent actions on the environments and the rewards received by other agents. So this is crucial for understanding and mimicking here the coordinated behavior of multi-agent system. Sequential decision making. Our Markov games represent sequential decision-making scenarios where agents make decisions over multiple time steps, considering the long-term consequences of their action. Strategic consideration. Markov games inherently incorporate the strategic aspect of multi-agent interaction, where agents need to anticipate and respond to the actions of the other agents. We will see this is the core of a MALICE algorithm. Then, of course, it provides us with some formal mathematical framework. Please go and read the original publication from John von Neumann, 1953. And we have a flexibility, and we can generalize this for tackle diverse MALE challenges I will introduce you a little bit later on in this video. So here we have now definition of Markov game and why it's so great. And now let's come here to our optimization topics. Now the goal in MALE is now to learn a policy sigma that maps the state to a probability distribution over action tuples that mimics now the behavior of expert policy as closely as possible. Remember, we have an expert and a student situation. And if you want to code this, if you want to operationalize this idea, you have one and now two criteria. The first, classical, we have the value equivalence. Now, what is the aim that we set out with value equivalence? We want to it's a minimization problem, an optimization problem. We want to minimize the value gap, which is, per definition, the difference in the expected cumulative rewards between the learned policy and the expert policy. And there's a beautiful formula, as you can see here. This is our gap definition. And our pi sigma e and our pi sigma simply denote the joint policies under the expert policies and under the learned policies of our student. And now to the new part, now to the intelligent part, now to the part where we have deviations suddenly coming in and where the system can learn new things. And this is now an optimization problem that we call a regret minimization. The researchers, I'm going to show you in a second, published this new criteria. Now, it is the same. Like in the value equivalence, now we are talking about a regret equivalence. And now we aim to minimize the regret gap. But this is something completely different. Because this reflects now, look at the formula here, isn't it beautiful? It reflects the worst case incentive for any agent in the system to unilaterally deviate from the learned policy, where our pi sigma phi I indicates the joint policy when one agent I deviates according to its own strategy phi I. This regret gap, we will spend a little bit later in the video 5-10 minutes really trying to understand what this formula means. Don't worry, you will understand it in a minute. Okay, Markov game. You see, now we have our framework. Let's have a look now what we are dealing with. Yeah, in green it's for my green grasshoppers. The policy, the mediator policy. So this is the policy the learner is trying to learn. It is a function that maps a state, as element of the set of the states, to a probability distribution over the joint actions. Let me give you an example. In a self-driving car scenario, the mediator policy might recommend a lane change and to change the speed to a group of cars based on their current position and the overall traffic situation they are in. And then we have a joint agent policy pi. This now describes how the agents actually behave in response now to the mediator's recommendations. And it also maps, of course, it has to be coherent, a state as element of S to a probability distribution over the joint actions, yes. But now our pi sigma, this is the joint agent policy where all the agents perfectly obey the mediator's recommendation. And then we have a pi sigma phi I, and this represents the joint agent policy where only agent I follows the deviation strategy phi I that is specific to this agent, while the other agents continue to obey the mediator's policy sigma. So you see the complexity is, the first step is simple. We just have one agent that says, hey, I have a great idea. I have a new strategy, a deviation strategy that is just a little bit off the mediator's policy, and I explore if I can find a better solution. Let me give an example. If the mediator recommends that one car slows down, our pi sigma represents the scenario where the car actually slows down, while the pi sigma phi I represents the scenario where the car decides to ignore the recommendations and do something else. Maybe not really speed up, because this would be the opposite, and we can define that it is doing something else, but it is an action that is close by the recommended action. So the system is not going crazy and saying, yippee! No, we want to develop new behavior, but on guidelines. And here we have a deviation strategy phi I. And this is now a function an agent I uses to decide how to respond to the mediator's recommendations. So it takes the current state as element of S and the mediator's recommended action for agent I as an input and outputs now specific actions. Let me give you an example. A deviation strategy for a car might be to always speed up if the mediator recommends slowing down. It's a little bit crazy, but okay. Or to switch lanes if the mediator recommends staying in the current lane. Now, in the publication I'm going to show you, they have now the phi I for an individual deviation strategy of one agent, and a capital phi I is now the set of all the possible deviation strategies for an agent I. Never mind the notation, the mathematical notation. If we understand the idea behind this, it is easy. Okay, next term is the value. The expected cumulative reward, or the utility that an agent I gets when it is following the joint agent policy pi. Now, this particular value is now a little bit complicated, so I tried to explain here all the different terms from the publication. I'm going to give you in a minute. And we have here the expectation over the initial state as 0, drawn from the initial state distribution of P0. The expectation over all the trajectories generated by the following policy pi, the sum of the rewards over the time horizon, and the reward that an agent I gets at a time step t in a state st when taking a joint action at. Jesus. An example, in a self-driving car case, value might be a combination of factors like the travel time, the fuel efficiency, and the safety for each car. This might be a combination that the AI system calculates to reach its optimal goal, and this is a safe journey from A to B. And this is the mathematical formula that we're going to code. Great. Of course, we need now the new stuff, the regret and the regret gap. The regret measures here the maximum incentive any agent in our pool has now to deviate from the mediator's policy sigma. And we have here a beautiful formula. We're going to look at this in a little bit more in detail. And I have given you all the elements that you see what it is. An example is simple. If a car could significantly reduce its travel time by ignoring the mediator's recommendation to slow down, the regret would be high. Now, the most interesting fact is, of course, the regret gap. But you see, this is simple. So this compares the regret of the learner's policy, sigma, to the regret of the expert policy, sigma expert. This is all there is to it. Or if you fill in here all the terms, you see that this simple difference becomes now, this is now our new code that will rule our new AI system. So this example asks here, how much more tempting is it for a particular single agent to deviate from the learner's policy compared to the expert policy? So this is important because up until now we had that the learner's policy is doing exactly what the expert is telling him to do. But we want the system to develop its own intelligence, its own impulse of doing something new, discover new path, deviate from the given path a little bit, not much, but just not do exactly the same. Discover new solutions that are close by and then just run with it. Okay, this was the regret gap. So coming back, we have now two main criteria in our formula. Just to remind you, the value equivalence that I already showed you in mail is about ensuring the learned behavior of a group of AI agents matches the performance of expert agent as closely as possible in terms of the outcome they achieved. Think of it as aiming to score as well as the expert in a game, where the score is determined by how well the agent actions meet the goal of the task. So we have here simple a performance match. But now comes the disturbing part, the beautiful part, the learn more than the expert knows part. We have now an optimization problem with a regret minimization. And this now deals with the concept of a strategic decision making that every little single AI agent has to do in our cluster of agents. So each agent is now considering not just to follow the learned or the advised action, but each agent has now so much agency, so much creativity, quotation marks, to explore other action as well that might lead to a better outcome. And this is a trial and error. There's nothing that knows this beforehand. This is just brute force of compute 1 million alteration to a particular action. So in MALE, minimizing the regret involves now ensuring that no agent feels a significant loss, if you transfer this to a human picture, a significant loss or a regret from not deviating from the learned policy. So you see, the idea is simple. We have now a new strategy and a performance match clause that we have to implement. And this is all there is to it. And a little bit of code. And you have already seen this in my other videos where I showed you about behavior cloning. And there's another methodology I have not yet mentioned, inverse reinforcement learning. But those were single agent IL algorithms aimed at minimizing the value gap, the first gap. But now we are moving to multi-agent imitation learning algorithms, and now minimizing the value gap is not enough. This is the new insight. Hey, this will not work. But you know what? Be creative. Because you see that in this video I showed you that we can combine the behavior cloning, this means the imitation learning, and the reinforcement learning, which are different, but we can build in on top of each other if it is necessary. And you remember, I told you, we want to make our next Mars rover more intelligent. So we have here on Earth a beautiful cloud computer center. We can simulate all the Mars actions and whatever is possible, whatever could go wrong, and develop here on Earth here countermeasures. What to do? Because our little device on Mars with an hour time delay, multiple hour time delay, they have to know what to do. So if we have now imitation learning, the little Mars rover imitates now the learning from the huge cloud computer center on Earth that is operating for a year to find all solutions to a problem, we can now use them to have a base model based on a diffusion policy that predicts an action chunks, a complex chain of actions that is trained on behavior cloning. And then on top of this, I showed you in the video, that we have now some residual models that were trained now with the reinforcement learning methodology to make now correction in each single time step on the rover. So you have the freedom to combine them whenever you see it fit, but you have to understand when you combine what with what goal. Beautiful. And yes, sometimes it's fascinating. Now you can bring all of this simple thing now to a multi-agent setting, but let's come back and focus here on a particular research I want to show you. And this is by Carnegie Mellon University. Some beautiful ideas here, published 6th of June 2024. Multi-agent imitation learning. Value optimization is easy. Regret gap minimization is hard. So those researchers here, some beautiful ideas, and this will be here, the content here going forward.